Well, good day, everyone. My name is Chris Good. I'm the Director of Research at the Conservation Fund's Freshwater Institute in Shepherdstown, West Virginia. My talk today is going to be on wrasse disinfection, the industry practices for disinfection, and some of the experimental evaluation that we've done for water disinfection at the Freshwater Institute. I just wanted to thank the organizers for WRASSTech for running this whole thing online in these trying times, so that is much appreciated. So I will talk briefly about the presentation outline here. So the first section I'll be talking about will be the bulk of this presentation. Actually, it's a survey that we ran with Norwegian and North American wrasse facilities to determine disinfection practices and any differences between and within regions for disinfection of wrasse. And this will move into the second part, which is Freshwater Institute research on water disinfection and water quality optimization. And finally, just a brief discussion of some of the future disinfection projects that we have planned later in 2020 and 2021. So as mentioned, the first part will be talking about this survey that we ran. This is called Disinfect. It's actually a very small component of a much larger research initiative, which is called Control Aqua. This is an 8-year multi-institute research coordinated event, and it's the Center of Closed Containment Aquaculture, and this is funded through the Norwegian Research Council. So the main organization in Norway is Nofima, but there are over 20 different partners, and the Freshwater Institute is the partner in the United States. And the overall goal of Control Aqua is to develop technological and biological innovations to make closed containment technologies reliable and economically sustainable. So it's really been an honor to be a part of this research initiative. I just want to give a bit of background on this. So a lot of the smolt production around the world, particularly in Norway, is going through a sea change right now, if you will, in terms of how things are operated. So essentially, wrasse is being adopted at a very quick pace, but also it's a matter of the size of the smolts and post-smolts that are being raised. Over the last 10 years, it's been realized that larger post-smolts, 300, 500 grams, even up to 1 kilogram in size, are considered a better route to make them more immunocompetent before they go out into the ocean. So that requires a massive amount of infrastructure investment, and industry is very keen on this, but they're also keen to understand this environment a bit more. This is a sort of an unknown frontier. So essentially looking at how to optimize the environment of these closed containment systems in order to produce quality smolts for stocking in net pens. So as mentioned, disinfect is a small component of this, but it's very important to understand what industry is doing in terms of disinfecting their systems. So you can see here, this is a collaboration between a Nofima scientist, Carlo Lazzato, and myself at the Freshwater Institute. So Carlo's near Aus in Norway, part of Nofima. And we set about looking at basically conducting a survey of Norwegian and North American land-based wrasse facilities in order to determine differences and similarities between the two. And with this in mind, with the information that is gleaned from this survey, hopefully this will spur on further research or the development of SOPs for a standard approach to wrasse disinfection that is efficacious and helps with the production of these facilities. So as mentioned, this was it was a bi-regional thing. It was in North America and Norway. So we sent out a number of surveys, and a total of 25 were completed and returned. And 16 of these were from North American facilities. I'm going to focus on the North American results, and then at the end of this portion, we'll go back and sort of compare what our findings with those of the Norwegian counterparts. So you can see from the map here, the bulk of the respondents were from maritime Canada, on the East Coast in particular, New Brunswick, Nova Scotia, Newfoundland. The Bay of Fundy area in particular is a large salmon producing area, but also on the West Coast as well. So some in Pacific Northwest of the United States and Alaska, and a couple on Vancouver Island in Canada, and a few inland RAS facilities, one in the Midwest, two in the Mid-Atlantic, and one in New York. And so most of these were Atlantic salmon producers, and a couple were primarily rainbow trout producers. And the bulk of them, again, were smolt or post-smolt producers, while a few were entirely land-based, so producing fish right up to market size on land. So I'll go through some of the results of the survey. We'll start with general disinfection. So this was more just the presence or absence of protocols and employees' attitudes towards them. So you can see here from some of these results, the majority of respondents, and the respondents were typically the production managers at each of these facilities. So the majority of respondents recognized the importance of standard disinfection protocols, and they actually had one in place, and employees were well aware of the standardized disinfection protocol. And also, the majority of these were considered to be there was a decent amount of compliance to what is in the protocols themselves. And interestingly, here we found that whether there was actual validation of the standardized disinfection protocols was a little varied. So some of them said yes, many said no or not sure. So that was an interesting finding. Also in North America, we found that there was a wide range of the age of the disinfection protocols. So some of these were less than 3 years, and some of them were greater than 10 years of age. And a few didn't actually know the age of the protocol, so one would assume that they are actually fairly old. Moving on to further results from the general disinfection component of the survey. So in terms of revising the program, or sort of monitoring it as a living document, so we found that the standardized disinfection protocol revision during the previous 3 years, the majority of these had done that, about 70% or so. When asked if there was a regular appraisal of these standardized protocols, most said yes. Interesting again is if the efficiency evaluation of the standardized protocol was evaluated, and most respondents said no or not sure. Also interesting was the fact that it was pretty much split between who actually had records of disinfection and those that did not. So a surprising number of facilities actually did not keep records of disinfection. And finally, in terms of attitude towards the protocol, these protocols are in place, and the employees are cognizant of these, but a good proportion of these protocols, there was no confidence or not sure in the confidence of these protocols. So, over half still were quite confident in them, but there was a significant amount of those that weren't sure or were not confident at all in the disinfection protocols that facilities use. So just to summarize this section, the key information to take away is for North American facilities, 15 out of the 16 that had been surveyed had standardized disinfection protocols. Among these 15 facilities, only 3 or 20% have protocols that had been experimentally validated. And a little over half of the facilities maintain records of disinfection practices, and a significant portion of respondents, again, they reported that there was either no or uncertain confidence in their disinfection protocols. Moving on to the selection of disinfectants. So this was very interesting. All the facilities, when asked which disinfectants they were using, all of them reported using multiple disinfectants. And the most frequently cited disinfectant in North America was chlorine, sodium hypochlorite, those bleach type disinfectants, followed by formalin, Virkon, and quaternary ammonia compounds. So we asked which chemical disinfectants were being used, but also why they were being selected. And it was universally cited, the most important reason why the disinfectants were selected was their actual efficacy against specific pathogens versus, say, the safety of it or the ease of use, that sort of thing. So efficacy was the #1 reason why these disinfectants were selected, followed closely by concerns about residuals, so environmental concerns, what's actually being dumped out into the environment post-disinfection. So when we asked how these were applied, we first looked at the disinfection of pipelines and tanks at facilities. It was interesting that 62.5% of the surveyed RAS facilities answered that they're disinfecting pipelines and tanks after every production cycle, which I found surprising, but I guess it makes sense. There's a significant portion of those that do not after every production cycle, and I think that's very much related to how tight the bioprogramming is at these facilities, and that there's simply a lot of places there simply isn't time to disinfect tanks and pipelines after every single cohort. Most of the respondents reported cleaning prior to tank and pipeline disinfection, which is a good thing to see because that is the correct way to do it. Cleaning is to remove all the organic debris and other matter so that the disinfectant can actually do its job when applied. And facilities that are cleaning prior to disinfectant stated that they are employing high pressure sprayers, mechanical scrubbing with detergent, or a combination of both. So that's fairly typical. 69% of the respondents answered that they consider the construction material in the selection of disinfectant. So again, there's multiple disinfectants at each facility being used, and that is often dictated, their application is dictated by what they're being applied to. So say fiberglass or concrete, stainless steel, even wood for that matter. So the respondents were cognizant of different disinfectants having different efficacy or more appropriate on specific materials. Moving on to the disinfection of ancillary equipment. So this is things that are beyond tanks and pipelines. Again, there's a variability in the disinfectants that were selected. There's a range of disinfectants. You can see here, again, chlorine and sodium hypochlorite, quaternary ammonia compounds, and Virkon were being the most common. And most facilities use more than one disinfectant based on the equipment that's being treated. And when asked about the frequency of disinfection, respondents, those that actually do have a standardized protocol, they responded that after every use of ancillary equipment, things are disinfected, but some disinfect every day, and some weekly, and some have no routine procedure at all. Finally, we wanted to see what sort of what sort of disease picture is going on in these facilities. And so out of the 16 that responded, only 5 of them had experienced any disease outbreaks in the last 5 years, which was very interesting to see. So no viral agents were listed as being responsible for the outbreaks. And about 80% of those that responded were solely bacterial. So Vibrio species, Yersinia ruceri, and Aeromonas salmonicida were specified in terms of the agent that they had to deal with. So that was quite interesting to see. So, some of these agents like Yersinia ruceri and Aeromonas salmonicida in particular, those would generally require some sort of biosecurity breach in order to get into a closed containment facility. So it was interesting to see that there's still a bit of work to do out there in terms of buttoning up a facility and preventing pathogens like those from getting into facilities. When we asked what was done after an outbreak, those that responded mentioned that disinfection was carried out immediately after an outbreak, and they used the same disinfection strategies as routine disinfection protocols. So there wasn't any specific disinfection protocol for disease outbreaks or after disease outbreaks. So I'll talk a bit now about some of the key similarities and the key differences between North American and Norwegian RAS facilities. So in terms of similarities, the majority have standardized disinfection protocols in both of these regions, but at the same time, disinfection efficacy or efficiency has not been experimentally validated for the most part. The majority of facilities continually appraise these protocols, so that emphasizes the dynamic nature of these practices. Efficacy against pathogens and user safety are the topmost criteria in selecting disinfectants, user safety being a primary concern in Norway. Different practices are used for different ancillary equipment. That means in terms of the type of disinfectant and what is actually being disinfected. Immediate disinfection is carried out after an outbreak in both Norway and North America. And in general, staff at each production site are trained well to perform these disinfection events, including the proper use of protective gear and adherence to specific occupational health guidelines. In terms of differences, most Norwegian facilities did not have a set of criteria to assess cleaning, disinfection, and rinsing strategies, unlike in the majority of North American sites. And there is significant variability in the practices for disinfecting tanks, pipelines, floors, especially regarding the specific disinfectant type, pre and post disinfection practices, contact time, among other things. And as mentioned, in North America, the big disinfectants are chlorine, sodium hypochlorite, and quaternary ammonium compounds, which is very different from the scene in Norway, where other disinfectants like peracetic acid and hydrogen peroxide are the most commonly used surface disinfectants. And so that segues well into the next portion of this talk, where we are going to be talking about peracetic acid in general and its use in industry, but also at Freshwater Institute and some of the research that we've done looking at its application as a water disinfectant. Now, peracetic acid is generally considered environmentally friendly. It's acetic acid and hydrogen peroxide put together under pressure and certain conditions to create peracetic acid and water, so it breaks down into harmless components. And it has a long history in water treatment and the poultry industry, actually cleaning poultry carcasses. But so this has been approved in Europe, in the European Union, for use in aquaculture. And you can see in this photo here, it's been pioneered in Denmark. So we have Dr. Lars Flemming Petersen and Dr. Henrik Henriksen, and they're helping out a farmer to investigate optimal application in a rainbow trout RAS facility. So this is applied directly to the water with food fish present. That is, as I mentioned, that's approved in Europe. It has not been approved for that sort of use in North America. It has been approved in the United States by the Environmental Protection Agency for use as a surface disinfectant in aquaculture, but it still has not been approved for use as a water disinfectant when fish are present. But we're very interested in this. We see the potential for this as to help the industry in North America. So we are very keen to look at its application and to sort of look at this experimentally in various recirculation system research projects. Initially, we were interested in peracetic acid because it was typically described as ozone in a bottle. So something that clarifies the water, something that has multiple impacts on water quality. So we wanted to test this out. As you can see from the pictures here, this is at Freshwater Institute. Top left, you can see an experimental RAS with ozone. The water is crystal clear versus a RAS with the same flushing rate, same feeding rate with no ozone. The water can get quite soupy. After a while, it's very difficult to see the fish. So in general, ozone improves a range of water quality concentrations, so you get lower true color. In terms of disinfection, it tends to lower heterotrophic bacterial counts. It also lowers dissolved copper, iron, and zinc. and you get greater ultraviolet transmittance and oxidative reduction potential, the ORP. So we wanted to see if peracetic acid could possibly be a substitute, or perhaps even used in addition to ozone, to help clarify water and to bring down bacterial counts in recirculation systems. And so this is, we had this study published last year. John Davidson at Freshwater Institute was the prime author on this. So there's the paper if you're interested in reading up on further on this. But we looked at peracetic acid, a continuous dosing or semi-continuous dosing of peracetic acid in experimental RAS with rainbow trout. It was quite a long study. We looked at doses up to 0.3 milligrams per liter. So that is enough to potentially have impacts on water quality, but not to harm the biofilter. Well, what we found was, like ozone, it increases the water oxidation reduction potential. However, we concluded at the end of this study that it really isn't a viable replacement for ozone. So there was actually very little difference in water quality compared to ozone, which has a much more profound impact. We found in terms of disinfection that there was really no significant differences in bacterial counts up to 0.3 milligrams per liter. So again, in terms of disinfection, it wasn't really a viable solution under those circumstances. So at that dose, but perhaps more importantly at that dosing regime, there has been some evidence that semi-continuous application might not be the best approach, that a pulse dose maybe once, twice a day or so might be a better way to do it versus this continuous approach, because others have found that semi-continuous application actually leads to increased biofilm in the systems. So I think that needs further research, but it was a very interesting finding from this study. So the next study that we performed was looking at post-vaccination saprolegniasis. So saprolegnia is a ubiquitous water oomycete. It's called fungus. Every aquaculturist has seen this at one time or another. And in industry, the Atlantic salmon industry anyways, when the fish undergo vaccination, there's a period of stress after that where the fish are particularly vulnerable to saprolegniasis. And so we wanted to see if we could apply peracetic acid post-vaccination to prevent saprolegniasis from occurring. So we cobbled together 12 experimental scale RAS. We used Atlantic salmon par from a USDA source. Unfortunately, they were 90 grams by the time we received them. We were hoping to do this on younger fish where vaccinations are typically applied, but it didn't work out that way. But anyways, we vaccinated all these fish with intercellular vaccination of a commercially available vaccine. So this is for Aeromonas salmonicida and a number of Vibrio pathogens. And then following the vaccination, we followed these fish for 6 weeks with pulse dose treatments of 0.2, 0.5, and 1 milligram per liter peracetic acid. And we monitored mortality over time. We did some saprolegnia water counts, although that didn't quite work out as well as we hoped. We wanted to see also if this impacted biofiltration. So we looked at the tan removal efficiency of the biofilters and things like just general observations of fungus and fish welfare, fin condition, and histopathology. So just going through some of the results here, you can see that there actually was a statistically significant difference in between all groups that received any dose of peracetic acid versus the control. However, if you look at the y-axis, you'll see that even though there was a statistical difference, we really weren't able to instigate an outbreak as we would typically see in industry. So there was even quite good survival in those control fish. So, and I think this comes down to the fact that we were vaccinating 90 plus gram fish. It would be very interesting to repeat this study with younger 20, 30 gram fish to see if we would be able to replicate what is seen in industry in terms of post-vaccination saprolegniasis. But that's a start at least. And the good thing was that in terms of biofiltration and that tan removal efficiency that we measured, there really wasn't any statistical difference among the biofilters, among any of the treatments. So there wasn't any noted biofilter impact with this study. As you can see, the standard errors are pretty wide in some of those treatment groups, and there was a fairly significant biofilter effect on this. But otherwise, we really weren't able to determine any differences among the treatments for TAN removal efficiency. When we're looking at welfare and fin erosion, hemorrhage and fungus on these fish at the end, we did notice just visible fungus, as you can see in the picture there. Those fish that received peracetic acid in general were much less likely to have visible fungus. And this may be related to the difference in survival that we saw, but it was very interesting to note that there was a statistically significant difference between those treatments. So if they received, basically the higher the dose of peracetic acid, the less likely, significantly, they were able to see, or we were able to determine saprolegniasis on these fish. And finally, I wanted to just discuss some of the results of a Sea Grant funded study. This is Wisconsin Sea Grant. Again, we're very interested in this, in mortality at early life stages. And in our experience at Freshwater Institute, Atlantic salmon fry, those are the less than 2 grams in size, are particularly vulnerable to opportunistic infections. That's when we tend to see the most mortality. And so we wanted to see if any of if peracetic acid at 2 different doses or hydrogen peroxide at a single dose, if those would remediate saprolegniasis or any other opportunistic infection during that sort of vulnerable fry stage. So you can see from the results here, we had mortality in all the groups, but those that were given a daily pulse of hydrogen peroxide at 15 milligrams per liter were had a significantly higher survival than those that received nothing. Peracetic acid had better survival, but not statistically better than the controls. And I should mention too that not only were the fish in that vulnerable period, but we actually stress these fish out every day with netting and holding them above the water for 15 seconds. So these fish were stressed, and to sort of amplify the situation to make it more susceptible to opportunistic infections. So that's good news for the use of hydrogen peroxide. It would be very interesting to run this study again with different doses of peracetic acid and to see if any of these doses, especially with hydrogen peroxide, if that affects long-term TAN removal efficiency of biofilters, because this study, unfortunately, was just done in a flow-through system. So I just want to wrap up this talk with some of our plans for the fall of 2020, getting back to Control Aqua and the Disinfect project. So we're moving on now to actual lab studies. And what we're planning on doing, now we're using all the disinfectants that were identified through the Disinfect surveys. We're going to assess a range of these disinfectants on replicated operating experimental scale fluidized sand biofilters. So we're going to get them up and running, have a proper nitrification, and then disinfect them with a range of disinfectants. Then see, following disinfection, the biofilter will resume the biofilter operation, and we will see how quickly, the length of time it takes for operational startup under these control conditions. And we're also going to assess the impacts of these disinfectants on biofilter microbiota and nitrification efficiency. So we'll be able to determine which, if any, of these disinfectants is optimal for disinfecting fluidized sand biofilters in terms of operational startup time and impacts on the microbiomes. So with that, I just wanted to acknowledge some folks here. So first and foremost, the Freshwater Institute team. Pictured here, we've got a great number of very high quality researchers and support staff, and it's great working at this institute. Also with NOFEMA, or the Control Aqua study, those involved in the Disinfect study, Carlo Lozado, Lil Heidi Johansson, Kevin Siller, and Osa Maria Eskmark were particularly involved in these studies. The last study I mentioned was through Wisconsin Sea Grant, so I wanted to thank Gregory Fisher and Jim Hurley for that. And our funders, we are funded primarily through the USDA's Agriculture Research Service. But as mentioned, some of this research was also funded through Control Aqua and Sea Grant through the University of Wisconsin. And I just wanted to wrap up by saying if anybody's interested in further details on any of these projects that I mentioned, my contact information is at the bottom of this screen. It's cgood@conservationfund.org. So please shoot me an email if you're interested, and we can discuss. And with that, thanks very much.